It's another lovely day, and I'm here with another lecture from organic chemistry. We said the third item that we need to look for it whenever we face an NMR spectrum will be integration, or the area underneath of any peak. And that area is going to tell you how many hydrogen you are dealing with. And the computer will do that one for you, so you don't need really to bother about it. And sometime, if we see overlap between peaks, manually we try to do the integration. So this sign, the sign that you see is representing integration, and you can draw it that way. And usually we write number of peaks like either on the top or at the bottom, wherever you see the chemical shift at the bottom of it, we write number of hydrogen atoms. Now, and the software, when they did this, got the area to the 27 and then decided to divide all those numbers by the 27, and because it's the smallest in the area, and the ratio we got one, this one can be treated as 1.5, here is 1, and that one is going to be treated as, again, 1.5. Remember, you do have error whenever you do integration. Okay, now we can have a fractional number, so we need to make a whole number. Software is going to multiply in all of them by same number, but it will keep the ratio identical. And we got 2, this one it will be 3, and that's going to be 2, and here we have 3 hydrogens. Okay, now, if I look to this area, I see the chemical shift is 2.4, and number of hydrogen equal to 2. Does it mean I have one, for example, CH2, just one CH2? The answer is no. Okay, you might have 2 of them. Okay, if I get 2 of them, then it should be 4 hydrogen. Why I say only 2? Because maybe you have element of symmetry. What do I mean by element of symmetry? Maybe you have a plane symmetry. Maybe you have something that can flip the molecule and make two sides of the molecule equal. In that case, because chemically they will be the same, you will see only one signal for them. Okay, let me, for example, let me show you this molecule and let's practice this example. Okay, so if I chop this molecule to half, and you'll see that this piece is going to be exactly equal to that one. So I should see only 2 peaks, one for this CH2. So I'm going to see a CH2 here. Next one is CH3. And what's the ratio between them? It's going to be 3 hydrogen to 2 hydrogen. Now, which one of them is going to show up in higher ppm? Okay, this carbon, because it's close to electronegative component or the carbonyl group, it will show up in higher frequency, in a higher chemical shift. So that's going to be CH2, and this one it will be CH3. Okay. Now, when it comes to like an element of symmetry, okay, again, what do I mean by element of symmetry? Like, for example, plane, like you can chop the molecule, or rotation, any excess of rotation. The more you have from those elements, the higher drop with number of signals that you will see. So if your molecule is really symmetrical, you will get a really small number of peaks. In this case, we have a molecule that is C5H11Cl. That molecule, I'm pretty sure, is saturated. How do I know it? I can treat the chloride as a hydrogen and go after number of possible hydrogen that I'm supposed to get for 5 carbons. So it says C5H12, and I do have 11 hydrogen and 1 chloride, so that's going to be 12. This molecule is saturated. Hydrogen deficiency index is going to be 0. So hydrogen deficiency index is going to be 0 because it's not, it doesn't have a pi bond or ring. Okay, next one is I see only 2 peaks. One of them says 9, the second one is 2. And we don't have a pi, so no pi bond, no ring. Yeah. And if I don't have those 2, so I'm going to say maybe this one is a CH3. How do I know it? If you see 3, 6, 9, 12 hydrogens, and they are showing underneath of 1 peak, that means you are dealing with methyl group, terminal methyl groups. Now, I see 2 hydrogen, so this one maybe represents CH2. Okay, but I see only 2 peaks. Now, let's draw the possible structure for this molecule. And hydrogen deficiency index 0, so no pi bond or ring, and I drew a bunch of actually isomers. And also, I highlighted number of the possible signal or expected signal for each molecule. We got 5, 5, 3, 4, 4, 3. None of them gives me 2 signals. None of them. Now, let's go back and check this. We have only 2 signals. How can I get 2 signals? Okay. We need to make some of the carbons somehow identical. How about this? CH3, CH3, CH3. Okay. Those, they will be identical. Okay. How do I know it? How do I know those they're going to be identical? If you treat all this hydrogen identical, then you have the right to replace any of the hydrogen by CH3 and say those hydrogen that attach to carbons are going to be identical because I treated hydrogen for methyl groups like I treat them the same, and I said they are chemically identical. So I'm going to say the methyl group is also chemically identical. That's one. And that's going to give me nine hydrogen. Next one is going to be CH2. And here I will put the chloride. Okay, now let's go after the sign. One sign. I see two hydrogens here. And what is expected, like what's expected the chemical shape for them? If you're dealing with just CH2 alone, it should be around 1 to 2. But if this one attached to halogen, okay, halogen, in that case, it will be 2 to 4. Okay, let's look at the peak. Where is it? Is between 3 to 4. So that's a sign that you have chloride attached to this group. Next one, those are going to be identical, and they will give you a signal for 9 hydrogen. And here you go. I got 9 hydrogen. So my structure is going to be a tertiary butyl group that attached to CH2, and then we will have a Cl attached to it. Another example, we have a C4H7Cl. With 4 carbon, I should get 10 hydrogen, but right now I have only 8. Okay, 7 plus 1 chloride will be 8. Okay, so clearly I have either 1 pi bond or 1 ring. Okay, 1 pi bond or 1 ring. And let's draw the possible structure, isomers or structures for the chemical formula that they give us, and highlight number of signals. I got 3, 4, 3, 3, 4, 4. And let's check how many signals we're supposed to have. 3, 2, 1, 1. So I have 4 signals. This one might be CH3. And it's between 1 and 1.5 to 2. Next one is, this one is 2 hydrogens. Okay, so that's CH2. And because it's really high, there's high chance attached to chloride. And how about the alkene? Where should I see alkene? Okay, or this hydrogens, those, that one. I should see them somewhere between 4.5 to 6. So I'm going to say those are alkene hydrogens. Now I need to talk about whether they are sitting in the same carbon or different carbons. Okay, so I see CH3 and CH2. Now let's go after a structure that they have methyl. Okay, which one has methyl? That has methyl. Okay, with 4 signals. Next one, it has methyl, but only 3 signals. So I'm going to ignore it. The first one, because only 3 signals, I ignored it. This one has methyl. And what else? Okay, next one, no. This one also has methyl. And the third, last one, it has 2 methyls. So in that case, I'm going to say the integration should be higher. So beside the integration, I see only 3 peaks. And because I see only 3 peaks, that's not my compound. Okay, now I need to pick my final answer between these 3. Okay, how can I, differentiate them? Let's go after the second sign. The second sign, it says we have 2 hydrogens that they are showing around 4 ppm. Okay, I need to go after a compound that it has CH2. Okay, which ones it has CH2? Okay, this one has a CH2. Okay, what else? Okay, top one, that one it doesn't have on the right side, but let's see, that one also has. Okay, so now I'm narrowing it. So that one got canceled. Okay, the rest, of course, I got them canceled. Now I need to pick one between these 2. Okay, where should I see this? The chemical shift for it is going to be between, let's say, 1 to max, maybe 2.5 or 3. And how about this? This one is going to be between 2 to 4. And actually, it's going to be a bit higher than 2, like way higher than 2. And so I have one that is hanging around 2. Next one is going to be hanging around, maybe we should say 3 to 4. Okay, and now let's go check the peak for those 2 hydrogen, because it's hanging around 4 ppm. So I'm going to say there is high chance my correct answer is going to be this one and not that one. Okay, and okay, I do have 1 hydrogen here and 1 hydrogen there, and because there is a bond here, those 2 hydrogens are not going to be identical. So I'm going to see different peak for each one. Okay, and so we have a CH2 here that is going to give us 2 hydrogens. We have, let's call this one HA, call this one HB. Those are going to be the alkene, and we have the methyl here. Okay. So again, how did I differentiate them? Through position of the CH2. Because it's hanging around 4, that means there's high chance we have a chloride attached to CH2, and that's going to be my answer. Okay. Now, can I say whether this one, for example, let's say, is a cis or trans? So we said, my bad. Versus this one. Can I differentiate them by the data that I have? The answer is no. You need really more data. And what type of data? I need to know what type of splitting we have here. Okay, like is it a single peak or split it? Next, what's the gap between those actually? And the splitting, like the splitting actually, or the split peaks. I need to know the gap between them. Okay, and this is gonna be subject of the next lecture. And for now, I'm gonna start the lecture here. And thank you very much.